Number 5 on the 2.6 to 2.9 exam review. Calculators are allowed for this problem, but I am not going to use them because I think we can do all of this without a calculator. Part A, we want the limit as x approaches negative infinity of a absolute value of 2x plus 7 over a 3x minus 5. Because all of these involve limits as we approach the edges of the graph, we can use that end-to-the-end FEPL to determine what our dominant terms are. So if we look at the top of A, we can see that the 2x is going to outpace the 7, whether it's in the absolute value or not. So the dominant term will be a 2x in the absolute value on the top. On the bottom, it's the 3x that will dominate. So now that we've identified what the dominant terms are, we're ready to start dealing with the absolute value. Remember, the absolute value will do one of two things. It will either leave the inside alone if the inside is positive, or it will take the opposite of the inside if the inside is negative. And notice that x is becoming more and more and more negative. So that means this inside value is going to be negative. So the absolute value of it, if I want to drop those absolute value symbols, I will have to take the opposite of the 2x. The x's will cancel, and I'll get a limit of negative 2/3. If I look at B, same sort of argument here, same approach. The dominant term on the top will be 6x in the absolute value, and the dominant term on the bottom will be a 3x squared. Now the difference with this is that instead of heading toward negative infinity, we're heading toward positive infinity. So in this case, the absolute value is going to have a positive number inside. So that means when we drop the absolute value symbol, we'll leave the inside alone. Now when we reduce, we get a 2 on top and an x on the bottom. We have something that is growing much, much faster on the bottom than we do on the top, so that will approach 0. We'll have 2 divided by gigantic numbers. That gets really, really small pretty fast. On part C, again, we will be comparing out on the left side of the graph the growth of a sine of x, which just goes up and down from negative 1 to 1, to a polynomial. The polynomial is going to outpace the sine, so that means we'll have numbers between negative 1 and 1 divided by gigantic magnitude numbers in the negative direction. So 1 divided by negative a trillion, that's going to get awfully close to 0. Part D is a little bit tricky because I've got my terms out of order. If I look at my top, I have an x to the 5th, a 3x to the 4th, and a positive 2. So the x to the 5th is actually the fastest growing term. If I look at the bottom, I have a 5x squared, and then I have a negative 4x to the 5th. So even though this is at the back, this is the one that's going to dominate. Now if I delete or factor reduce my x to the 5ths, I end up with a negative 1/4 as my limit. Now, because we've got so many of these, I'm going to switch pages and move on to E through H. Same thing, no calculators are necessary, so I'm not going to waste the time getting it up here. I'm approaching negative infinity. I look for the dominant term. The dominant term on the top is a 3x cubed. The dominant term on the bottom is a 20x squared. So if we look here, I can reduce, and I'll end up with a 3x on top and a 20 on the bottom. Well, now in this case, I have a polynomial over a constant. The polynomial is going to far outpace the constant, so it will dominate. So the question is, what happens with this term as x becomes more and more and more negative? Eventually, it will go to negative infinity. F and G are both a little challenging because we seem to have trouble when we're working with exponentials. So the first thing I want to do is I want to remember that if you have the same base on top as you do on the bottom, that what you really have, if you use your old exponential rules, is that single base raised to the top power minus the bottom power. So that means we're looking at the limit as x approaches negative infinity of 3 to the negative 2x. Now I know some of you had a hard time figuring out whether that grows on the left or on the right. So I'm going to rewrite it again using properties of exponents as a 3 to the negative 2 raised to the x. Well, that's the same as a 1 over 3 squared raised to the x, which in turn is the same as a 1/9 raised to the x. So now we've identified that our base is a number smaller than 1. That means the graph is going to grow on the left side and get flat on the right. So if we look at part F here, we want to hop on the curve and move to the left. If I move to the left, I'm going to be heading up. So this particular limit will be positive infinity. If I look at G, notice that it's the exact same function, except now I'm heading to the right. So if I head to the right on this function, I will be looking at the flat side of this 1 over 9 raised to the x power. And the y coordinates on the flat side are getting closer and closer to 0. Last but not least, we have this limit as x approaches negative infinity of sine of x over x. Well, and there's not even over x, I lied, just sine of x. So if I look at sine of x and I think about what's going on the left side, we can see that it never gets close to a single value. It just keeps oscillating over and over and over. Because of that, we say that this limit does not exist. There is no one y coordinate that the sine graph gets close to, no matter how far out we go on the left-hand side.